So my name is John Studarus. I'm one of the US OpenStack ambassadors. These slides, I've got them online in Google Docs. So you can take a picture of this QR code and download them. That's probably the easiest way to get access to them. I'll display this again at the end if you need it. Okay, so a quick little bit about me. I'm an OpenStack US ambassador. It's basically a volunteer position with the OpenStack Foundation. So I help user groups across the US run events. I put together training sessions, tutorials, give presentations like this. I also run one of the OpenStack Clouds that's used by the Zool project. So it's a volunteer cloud, it's donated equipment, and then we run that and provide computing resources that Zool uses through Nodepool to do a lot of the OpenStack CI work. Happy to talk about that. I'm president of JHL Consulting, provide various cloud computing services. So going back to the Zool cloud, a couple of years ago I got involved with Packet Host. They're a bare metal service provider. I contacted them to ask them about providing hardware resources to build OpenStack clouds that we could use within the user groups so that we had clouds available for people that wanted to test things out. We could do tutorials during user group sessions and basically just having environments. So Packet was kind enough to provide the computing resources for that. And then about 3 months ago, they approached me and said, hey, is there anything more we can do for the OpenStack community? And that's when we got into, hey, let's start up and run a cloud and make it available for the Zool project. And so that's when we got involved running one of the OpenStack infra clouds. Since then, they've said, hey, we want to get more involved in OpenStack. We have these new ARM-based systems. Can you let us know if they're useful within OpenStack? And that's what sort of got us into this, this next project on how OpenStack can run on these sort of next generation processors and the benefits behind that. One other thing I want to talk real quick about is City Cloud. They're kind enough to sponsor a lot of the events in the US. So they've been kind enough to give me some $750 credits for City Cloud. So if you'd like to get one of these, come see me after the presentation, and this will you'll get hooked up there and be able to try out some OpenStack public cloud. Okay, so a little bit about ARM, what it's all about. Most people hear about ARM processor and the ARM Foundation. It started out as processors for cell phones, so lower power, lower CPU capabilities, smaller form factors. So since then, it's grown up. We have full-fledged computer systems, 96 cores, full rack-mounted systems that are ARM-based. They've really started coming up to speed. Key attributes about them is they are low power, so they use considerably less power than an AMD or an Intel x86 system. And as such, they don't need air conditioning. You can cram a lot together, so much smaller form factor. So in data centers, this makes sense because you can fit more in, and then they use less power and require less air conditioning. But it's also an ideal for edge locations. An edge location might be a satellite office or a telco head end or a car or a train where there might not be a lot of power available or air conditioning to keep the computers cool. So ARM processors sort of fall into ideal processor type for edge locations. So the question was, well, so we have these ARM processors. How can we go about seeing if OpenStack works using the ARM processors and what we can do to build out an edge cloud using OpenStack on these ARM systems. Okay, so first let's talk about the edge. What is the edge computing all about? What are the ideas behind it? And there are many different versions of edge computing. If you talk to different people, you're going to get different answers. So China Unicom, this was a presentation they gave at the Vancouver Summit. They talked about their model for edge computing and what they are planning on doing. So as you can see here, they're moving from large centralized data centers into edge and access data centers. And you can see that the latency time down at the bottom there, they're moving from 50 milliseconds down to under 10, 2 to 5 milliseconds. And even if you have a device that's local within a house, to less than 1 millisecond. That's really what people are talking about when they talk about edge computing. It's bringing devices closer to the end user so that latency time is reduced. You get faster response times rather than having to go all the way back to a central data center. So locations could be telco head ends, factory floors, satellite offices. So Verizon has started deploying OpenStack in a edge configuration. For them, what they're doing is they have white boxes that they call a micro CPE. CPE stands for customer premise equipment. So actually computer gear that they install at the customer's location. So in this case, here it's a customer's satellite remote offices. And the idea is that right there in their satellite office is an OpenStack compute node. And Verizon, from their dashboard, is actually pushing compute nodes and processes directly onto that box that's located on the customer's premise as an edge device. So another definition of edge computing. Packet, who's been gracious enough to donate the equipment, their vision of edge computing is smaller regional data centers. So data centers, Hong Kong, Seattle, Singapore, Sydney, Toronto. The idea is you bring these, you have more data center locations. Ideally, they are going to be closer to the end user and have faster latency, better response times by bringing these data centers closer. And then we've got autonomous cars. So the idea there is you need low latency because the processor on the car needs to be able to respond very quickly. And it might not have the time needed to go back to a data center to do some data processing and come back to the car. Or it might not even have the connectivity to go back to the data center and back to the car to respond to something. So in this scenario, the edge is actually in the car. Trains are similar. So the actual processing, the compute node in the case of OpenStack, would actually be in the car, in the train. And it would need to work in a way where it can disconnect from the network, disconnect from the control plane, and keep on functioning okay. And then when that network connectivity comes back, be able to connect back into the OpenStack control plane and sync itself back up again. Okay, so we got 4 different definitions of edge computing. So let's take a look. Is OpenStack ready? Can OpenStack sort of address these use cases? And what do we need to do to update OpenStack to be able to support them? So the first thing we talk about is the scheduling filters within OpenStack. So the OpenStack controller, every time it gets a request for a new compute node, for a compute instance, it goes through, takes a look at all of its compute nodes that it has available, and it makes an intelligent decision on where to start up that virtual machine, where to start up that instance. And it uses things like, well, how much RAM is available on the machine? Is there a CPU available? Are there other machines running on that compute node? Maybe it's overtaxed already and I shouldn't run it there. And there are various filters that you can put in. So you might even say that you don't want 2 virtual machines being run on the same machine, or that maybe you do want 2 virtual machines being run on the same control node. And those are called filters that are programmed into the scheduler. Well, we need some new sort of next generation edge computing type filters. We need to introduce them into OpenStack. So one here, latency, a filter that goes through and you tell it, hey, give me a compute location, give me a compute node to start my instance that has response time at less than 10 milliseconds from this IP address or from this AS number. And OpenStack will then go and make a determination of where the best location is, or maybe by geopolitical boundaries. Hey, this data needs to stay within the EU or stay within China. And once again, OpenStack uses that as a scheduling mechanism to go through. Or facility. Hey, I need this compute power to be on this factory floor, or I need it to be in this remote office, in the case of Verizon, and it would go through and roll it out there. So these are the type of filters that need to be built. We need to think through how this is going to be done and get it put together and installed. Sorry, computer turned off for a second there. Okay. So the other things, the actual compute nodes themselves we need to go through, and we need to update them and make them work for edge computing. They need to be self-sufficient. In case they get disconnected from the control plane, they need to keep on running. Self-healing, when they connect back onto the control plane, we need to make sure they can sync themselves back up to the control plane, and then even continue operating and doing control plane duties when they are offline. We need to make sure that they are efficient with the computing resources. So these edge locations, we're not going to have a lot of space, we're not going to have a lot of power to install a lot of processors and have a lot of RAM and a lot of storage. So we need to be efficient with the computing resources we have there, and even tune down the controllers so they're not using a lot of the computing power and making sure that it's available for the compute nodes. We also need to make them physically smaller. These satellite edge locations are not going to have a lot of space. If we're putting this compute node into a car, we need to make sure it's a much smaller form factor than your traditional 19-inch rack system. And maybe even a type of unit that's going to be able to run without any air conditioning. A lot of remote offices, factory floors, not going to have air conditioning out there, so they need to be low power. So ARM solves a lot of that. Okay, so a lot of that isn't done yet in OpenStack. It's work that still needs to be done. It's being thought through by the various working groups. There are white papers being written, trying to figure out how to get that done. So that's the bad news, that there's work to be done on that. But let's talk about the good news of what has been done and what's worked. So let's talk about actually running OpenStack on top of ARM-based systems. So Cloudflare. Cloudflare is a CDN, a content delivery network. So Cloudflare is actually one of the largest ones. They might actually even be the largest. They went through and they realized that replacing all of their Intel-based systems, x86 systems, with ARM-based systems, they save enough money in all the data center costs of space and power to go through and replace all of their Intel systems with ARM-based systems and end up saving money on the whole process. So they went ahead and did it. They went ahead and replaced all of their Intel systems. So we got a couple of slides here that go through and talk about it. So I'm just going to read it through. So excited about Qualcomm Centriq. Qualcomm is a manufacturer of ARM-based systems. They're ARM server chips. On Cloudflare workloads, we're seeing equivalent power to Intel's equivalent performance to Intel's at half the power. So the same workload is being done, but half the amount of power is being consumed by the device. So this has a couple of wins. You're using less power, right? But every watt of power you're generating, you need to have air conditioning to go through and cool it, right? So that also means they have a win there because they can use less power driving the air conditioning units to keep the systems cool. So they're seeing a double win there. So big win for Cloudflare. So the question is, hey, if Cloudflare can do this and they can rip out and replace their entire worldwide network, can we do the same thing with OpenStack Clouds? So here's what we did. We took ARM systems from 3 different vendors, so Cavium, Huawei, and Qualcomm, and we built out multiple cloud configurations using those 3 different ARM-based systems, and we baselined it against an AMD EPYC system. So here are the specs. The TDP is a thermal displacement, basically how much power, maximum power the units will use. As you can see here, the AMD uses 155 watts versus the Huawei is down to 110 and the Qualcomm's down to 110. So less power is being used there. The number of cores. On the ARM systems, you'll typically see way more cores than you'll see on an equivalent Intel or AMD system. And the idea is that scaling up for an ARM system is being done by actually scaling out and using more and more cores, as opposed to the x86, where if you need to scale up, you increase the frequency, the processor speed. So you'll see when you take a look at ARM systems, you'll see way more cores, which is good for OpenStack because OpenStack can use all of those cores by running more virtual machines. And then I took just the stock OpenStack installer, vendor agnostic. You go to docs.openstack.org, and just those are the instructions I used to build out this cloud. And then the equipment donated from Packet. So Packet had all of these machines available, set them up, and Packet has an API you can hit that actually provisions the machines. So I was able to build out a Terraform configuration file to quickly and efficiently, in about 15 minutes, I was able to go through and build out each of these clouds. So here is just a workflow of what it looks like when Terraform runs. So the output of Terraform, it displays all the IP addresses and username and passwords to log into the OpenStack environment. The beauty with using Terraform here is that I could deploy all of these systems. I could identically, every time I reran it, I could switch from Qualcomm to Huawei to the AMD system totally easily and know that I would get identical configuration deployed. So no worrying about human error. And like I said, in 15 minutes, I can get a full cloud environment spun up. So I spun up a minimum of 3 nodes for each of the different ARM-based systems, a compute node, a controller node, and a dashboard. And then I also spun up a cloud that's a combination of both AMD and ARM-based systems to make sure that the systems could work together if you wanted to have a combined cloud of 2 different processor types. So here's sort of the output of just running a typical OpenStack compute service list. We can see that there are all of the services running. And in this instance here, we actually have 2 compute servers running. One is an x86, and one is an ARM-based compute server. The ARM processor is not binary compatible with x86. So if you start up an ARM-based workload, if you start up an ARM-based virtual machine, it needs to run on an ARM-based processor. Same thing with an x86. If you start up a traditional x86 one, you need to have an x86 compute node somewhere on your network. And I just hear the details on different clouds that we spun up. Okay, so that said, did it work? You know, what did I have to do to get the stock OpenStack to work? Well, there were some changes I had to make. So if you just follow the instructions on openstack.org on some ARM hardware, it's not going to work for you. So I've given this presentation in the past, and people have come up to me and said, you know, I tried it, it didn't work. This is very helpful. So the stock installer, the stock instructions from openstack.org do hardcode in x86 binaries. So at CD, it's hardcoded in for x86, so you need to go through and check for that and replace it. There are some additional firmware images. You do need to make some changes to the compute switch over to KVM. You do need to have firmware images defined in the images that you create. And interesting enough, ARM systems do not have VNC support, so you need to install some additional software so you can access into the console on those machines through the serial. So all of these instructions here, I have made them available in GitHub, so you can log into GitHub and you can take a look at what you need to do to get an ARM-based system up and running. But net result was able to go through and get multiple VMs running of both x86 and ARM system running in the same cloud. They can communicate with each other across virtual networking. If you start up an x86 instance, the OpenStack controller scheduler is smart enough to know that x86 VMs need to start up on x86 compute nodes, and ARM instances need to start up on ARM-based compute nodes. So big win there. Okay, so next, now that I got my clouds up and running, I want to do some performance testing. I want to make sure that things work correctly and they work efficiently. So just like the last speaker mentioned, I used Rally to go through and do this testing. So tested 2 basic functionalities. Keystone, so issuing a token, adding a user, removing a user, as well as some compute capabilities. So starting up a VM, tearing down a VM, getting a list of all the VMs running. So my requirements for something to pass is each call needed to complete in less than 4 seconds, and then no errors were allowed. So all of these systems went through past the service level. So no errors, all the systems, all the commands finished in less than 4 seconds. So performance did vary across different machines. Some machines were faster than others. This is sort of a contentious subject, you know, when it comes to one vendor or other. But the ARM systems are always getting faster. When you start going through and you compare in how much power the ARM-based systems are using in comparison to the performance, some of these ARM-based systems, from a performance perspective, they are performing at the same level as the AMD system, but they were using less power. So sort of interesting there. So matching up with what Cloudflare was seeing when they went through. So end result is it does work. You do have to go through, make a couple of changes to get ARM-based systems running. Okay. So is this all? This is all available online up in this GitHub there. So the instructions here, you can go to GitHub. It's the whole Terraform is available. You can go through, run it. There is a website that has been set up. So www.worksonarm/OpenStack, and the team at Packet put together this website here. It has a link on here over to GitHub. This website here, does have a little link to get $25 worth of credit to go through, and you can spin up this environment and run it. I believe each machine costs 50 cents to run, so if you spin up a 3-node environment, the machines vary from 50 cents an hour to $1 an hour. So if you do the more expensive ones, it'll cost you $3 an hour to run an OpenStack Cloud, which is a great deal. You can run it for however long you want, run the Terraform, give it a try. Load up some ARM-based systems, load up some x86-based systems. The configuration file, you can change the configuration file within Terraform to do a mix of however many compute nodes that you want. So you can scale it up however much you want. So feel free to give it a try. I'm always happy to hear feedback on what things work, what things don't, what other things you'd like to see. Okay, so end result. Edge computing, still work to be done at OpenStack. Verizon's done a little bit of work. They're already deploying things, but really we need to add more capabilities within OpenStack to really tackle the edge. But the ARM-based systems are there. They're ready to go. I think there's a lot that can be done there to get that running. And here's the link to the slides again. Any questions or areas that I can explain a little bit on?
So you mentioned about the scheduler
Sure.
for the edge environment, and do you assume that there's the single OpenStack cluster in the center and the distributed compute node on the edge, or do you assume that multiple cluster on the edge and like central scheduler on top of it? Or what are the architecture you assume?
So I think there's going to have to be some sort of compute capabilities at the edge. I think the edge needs to be efficient enough to be able to do some basic sort of controller duties. Where the scheduler lives, I think probably there's going to be some central spot that has a gigantic view of all the resources that are out there. And when you start talking about all the resources that are out there, it could be a variety of different resources. It could be different public cloud providers. It could be different bare metal service providers. Maybe some of them are on-demand public clouds, and maybe some of them are private clouds. So, yeah, I would envision there's some sort of centralized view of everything. But the things like starting up new instances is something that could be done sort of autonomously at the edge. If it finds it needs to do something like that, rather than having to go all the way back to the central location where maybe it doesn't have connectivity all the way back.
Thank you.
You want to see the QR code of this slide?
Oh, the QR code, sure.
Okay, any question? regarding the edge computing on ARM. So I have a question about the edge computing. So I heard about the edge computing from the telco service provider point of view about the VNet running on the edge cloud computing, edge computing. So have you tried to deploy or run any so some kind of network sensitive in the OpenStack ARM?
So say it once again.
Have you tried to deploy any VNF with the network function or something else that requires a low network latency and something else in ARM?
There are applications that do require low latency.
Yeah.
So for example, the automobile, it needs to be able to respond very quickly back.
Yeah.
So if you go back to the China telecom slide, you can see sort of the latency requirements or the latency capabilities of how close things can get. So you're wondering about a virtualized network function, where that might get put in?
Yeah, can run on the ARM.
Yeah. I mean, if we talk about what Verizon's doing, so Verizon has this OpenStack white box that's basically a compute node that they put at each location.
Yeah.
And it basically runs, firewall services, VPN services, and you go to a centralized dashboard and you configure it, and then it pushes those services out to the edge locations. So, you select which edge locations that you want, and it goes through and it configures those boxes for you. So their vision is that those network functions would happen at that box at the remote office. So might as well do the firewall there rather than having the firewall happen back in a data center, so the traffic doesn't have to traverse back into a data center.
I already see the keynote of the Verizon in OpenStack Summit in Barcelona or Boston, right?
Yeah, in Vancouver, I think they've given it a couple of times.
Yeah, but I not see the real demonstration of the CPU of Verizon. So, and I'm very concerned about the performance of the application running on the ARM on the edge. So that's why I want to ask about the question whether you have run the real VNF or something else that can prove it can be running on the OpenStack on ARM.
Oh, on an ARM-based system?
Yeah.
Yeah. I don't believe the Verizon systems are ARM-based systems. Yeah, I believe those are x86-based systems.
Yeah.
But like I said, ARM-based systems come in a variety of different sizes. A lot of times people think of ARM-based systems and they think of a Raspberry Pi, right? But the Qualcomm systems, the Centriq systems, the Huawei systems, those are large-based. Those are 96 cores, SSD drives, so they got plenty of capability to go through and run workloads like that.
And the last question, can you come back to the slide of some CPU in ARM?
One more time?
I see that you list down, next. Yeah. So my question is, how about the price?
Oh, the price?
Yeah.
Sure. I have another slide with the prices. Hold on a second. Oop. Yeah, okay, so this one's got the prices on it. Can everyone see that? Yeah. So the price that you see here is the actual combination. This is if you wanted to go and rent this machine for an hour. So it covers the cost of renting the machine, the hardware, as well as the operations cost of power and everything else like that. So you can see that so you can ignore these first two ones here. So what I showed on our slides were these machines here. So the AMD system was $1 an hour, and then the Cavium was 50 cents, the Huawei is 50 cents, and the Qualcomm is $1 an hour. So the Qualcomm is the same price as the AMD system. And if you take a look at the performance, so you get pretty close between the AMD and the Qualcomm systems. And these were sort of first generation systems. I know that Qualcomm I know there are much faster systems available now on the ARM-based side. So these are the prices that if you just go directly to Packet and click the button, that you're charged for those systems.
Okay. Okay, so any question? Mọi người có câu hỏi gì không ạ? OpenStack chạy trên nền tảng ARM.
Has anyone tried to run OpenStack on an ARM-based processor?
I guess no one.
Raspberry Pi? No.
Okay. Vậy là không có câu hỏi nào. So, okay, so I think we are done.
Okay. Like I said, I do have the credit, so if people want to come up, I can hand these out.
Yeah, so nếu mọi người bạn John, bạn ấy đến và có mang những cái coupon $750 sử dụng dịch vụ của City Cloud và mọi người có thể đến trao đổi với bạn ấy. Nếu bạn ấy thích thì bạn ấy sẽ tặng cho mọi người một cái $750 và em có một cái. Thì nói chung là nói chuyện với bạn ấy thấy cảm thấy thích của bạn ấy thì cái đó nó khá là hay. $750. Đấy. Thì gọi gần như kiểu pitching. Okay, so we are done. Thank you. Cảm ơn mọi người. Session cuối cùng của chúng ta đã kết thúc. Còn một session, xin lỗi. Yeah. $750 thì cứ theo ra gặp bạn ấy và nói chuyện vài câu bạn ấy thích là